I discovered that the list monad has 4 different transformers. This is surprising. Hello. But,
Are they?
Surprisingly many or surprisingly few?
well, it's many. So usually it's not cannot be so high. There aren't so many examples of monads that have different transformers. So, but
Sorry,
the list
What is a
monad,
monad transformer anyway? Is it something that sort of like adds another monad into an
Oh,
existing one?
a monad transformer is a functor in the category of monads. So it transforms one
Okay.
monad, any given monad, into another in a certain way by adding features that you need to add. So you have some features, you want to add them to a given monad. So you take a given monad and the functor will transform it to a new monad, which has the old features as well. But it also has the new features. So that's basically, and there are some other things it has to do. Like you should be able to run this monad into something so to execute, to get the value out. So, but anyway, that's the gist. So basically, if you wanted to, for example, if you have a state monad, and you wanted to add the feature of the list monad to it, so then you need to take a state monad transformer.
Be right back. I'm listening.
And then apply it to the list monad. That's so the state monad transformer is this functor that takes any given monad and adds the state functionality to it. So then you can have all the other operations that you had before. And now you have an operation get and set. For example, you can implement it in this way. Or you can take the list monad transformer and apply it to the state monad.
Do you get the same thing?
No.
Well, didn't think so.
Because so it's, for example, the list monad can be used for non-deterministic computation, where you have several possible answers. You don't know which one is the real one, and somewhere at the end somebody will choose which one is the real one, but you don't know that during the computation. So list on states means that you might either update your state in the same way for each of the non-deterministic choices, or you can update it in different ways for each non-deterministic choice. There are 2 different inequivalent functionalities. So, and there are other. So usually it's not equivalent. In some very simple cases it is equivalent. But usually each monad has a single. So what does it mean to have a transformer of the list monad? It means that you're adding the functionality of the list monad to a different monad. So for each monad, there is this functor, which adds this monad's features to an arbitrary other monad. That's not a theorem. Nobody knows how to prove that. But you have a mapping from monads to these functors. You don't know. But there aren't any examples where people don't know how to find that functor. It's kind of, I'm skipping some here, but that's basically that's what it is. Anyway, so usually there's only one way that you can choose this functor, but in some cases there are many ways, and the functors. So there's a simple way, then there's a very, very complicated way, which has a lot more stuff. It adds not just the features of your monad, it adds a lot of other stuff that you don't really know what it is, but it adds that. So for example, there is some monad called the logic monad, which includes backtracking in the non-deterministic computation with search and backtracking. Using that monad, you can implement prolog, basically. So that monad is obtained in a very, very clever way. Nobody really understands except the authors of the paper. But it turns out that this monad is is a transformer for the list monad because it's just another way of implementing non-deterministic computation. You also get backtracking. You didn't ask for backtracking, you get it. But the transformer doesn't tell you that it only adds what you want to add. So this functor tells you it will add, and that has a certain law that has to satisfy to show that you're adding it. But that's all. So anyway, I was very surprised that you can basically you have very complicated constructions that nobody really knows how to use very well, but they're discussed in Stack Overflow, so people know about it. Anyway, so that's my discovery so far.
Well, could you share the link from the discussion of Stack Overflow in the chat, if possible, please?
Yeah, sure. I'll do that. I'll do that. Okay. Well, I don't want to derail the discussion. It's already 15 minutes. So I'm sure everybody has spent this entire time during Thanksgiving to read my book. For reading my book, because it's the best way to spend Thanksgiving, really.
Yeah.
Pretty close.
I have a comment about some of the subtyping stuff.
Yeah.
One thing is just, I guess, I don't know if it's a typo, but it seems like you're saying that, where'd it go? That the nothing.
It's a typo. We
Did we already do that?
yeah. Well, somebody alerted me to this.
I think, yeah, there's it's backwards. That one. Yeah.
It was
Right.
it was switched. Yeah. So
Right.
nothing is a subtype.
Okay. I thought maybe I was just, yeah, but sort of my comment is more on the notion of a subtype being a conversion, involving a conversion function.
Yeah.
And I mean, the way I think of it is just the compiler really arranges when things are one is a subtype of the other. It arranges that the one object can just be used in the super type, and there's
What does
no
it mean that it
conversion.
can be used? So that is the thing. Every book about this says these words. You can use a value of type A instead of a value of type B. What does it even mean? Are you switching off your type checking temporarily or what? How can you use that? You can't. You can't.
No.
You're
Yes,
not
you
supposed to
can.
do it.
In general, a term can have more than one type. Types are not inherent in terms. They are things that a type checker can check. Is this
Types are assigned to terms,
Yes.
and you can
Yes.
assign more than one type.
not usually at the same time to the same term, but well, I guess with subtyping you can.
No,
sort
that's
of-
what it is. So you're supposed
Yes.
to have a term of type A, and you're substituting it into an expression that requires a term of type B. So what does it mean that you can use it?
Well, is the term of type A also a term of type B?
Right. So that requires you to specify in great detail your type checking procedure, so that there is something else, some information about the term that you examine in order to determine whether this term has a certain type or not. Right? So and well,
No, the term already has a type. You don't have
no,
to check
wait,
anything.
it doesn't have the type because we don't know which type it has. It sometimes has one type and sometimes another,
Or it has both.
or it has both. So
Right.
it is not quite good to say that the term has a type. It doesn't necessarily have a single type. So there might be one or more types that it has, and we need a procedure to determine that. Right. So what would that procedure be? And then you have to specify what that procedure is.
But it's not a runtime procedure. It's
No.
it's
No.
just
It's not a
compile
runtime.
time.
Correct. Yeah, that's right. Yeah.
Right.
So
I mean,
you gave an example, Peter. You wrote in Slack, right? So you gave an example where you have a record, and you have more fields in the record or fewer fields in the record, and you can always ignore some fields, pretend that they don't exist, or and so on. So then you have the same record term. It could have many different types, depending on which fields you choose to ignore.
Right.
Like a forgetful functor kind of thing.
Yeah, so you can ignore all kinds of things. You can ignore some parts, you can ignore more parts. And so all of that is legal, but you have to specify this. So some languages don't do that. So in some languages, nothing is a subtype until you say it is a subtype. You have to say explicitly that something is a subtype of something else. Nothing is automatically a subtype. In many languages, right? So
especially with nominal types.
Well,
right.
I mean,
Structural
what I'm saying
types,
is that
you can figure it out. Nominal types, you usually have to say.
what I'm saying is that in many programming languages, there isn't only one option, which is you have to declare that something is a subtype of something else. And so nothing is really being inferred. It's probably going to be checked to some extent, but not really. So because in most languages, subtyping is not sound. You can break the type system, like in Java, for example. And so you can write code that type checks because subtyping works in this way, but then it actually gets the wrong type. So
well, yeah. Anyway. I think that's a bug, but anyway, yeah.
But so what I'm trying to do is I'm trying to define kind of more concretely what is the common ground between all these situations. So you can have a nominal subtype, or you can have a structural subtype, or both in the same language. But what is a common ground? So my common ground is you're supposed to be able to use a value of type A in a function that takes arguments of type B. Let's take that function to be identity B to B. Right? What you get is a function A to B. What does that function do? Nothing. It's just identity that reassigns types. Right?
They're always the identity, right?
No. It's not. You don't know. Your language somehow defines this. But what I'm saying is that from the way that your language has defined it, you know that you're allowed to use values of type A in functions that take type B as an argument. And so you do that with the identity function, and you get a function that takes A to B. And that function is unique.
Yeah.
So in other words, all these languages has a unique function type A to B. I call it the conversion function. That's it.
I know you do. And I'm just saying I mean, one example of where that gets awkward is like if you have B is a subtype of A, and then you have a list of B's, and you pass it to a function that wants a list of A's. What happens? You have to go through are you going through the entire list and F mapping the conversion function over all those elements and creating a new list to pass? That's not what happens.
No, that's a no.
Right?
Yeah,
it just passes it because the compilers arranged that the B's can just have the A structure.
Well, I know, and that breaks in Java, for example. I believe that the counterexample for type unsoundness in Java, it uses arrays of object and arrays of some type. Because any type is a subtype of object, well, at least the box type. So when it's a subtype of object, and then something, I can't remember the details, and then you essentially have a runtime exception because the types don't check, but at compile time everything seems good. So so that's, I mean, but I say yes, let's F map the conversion function over the list, and let's pretend that we are assembling a new list, and let the compiler remove that from our code as an optimization. And that's just, let's think more simply about subtyping. Subtyping is not some magic property of something. It's just an extra function that you're allowed to use. That's very easy, very conceptually simple. And now you can say, well, that's not
Mm.
how it's implemented. No. But then you can say, for example, automatically you get subtyping for covariant, contravariant functors. You understand how that works. You don't have to specify how that works. You just know how that should work. And then you say, in this situation,
Yeah, I don't know that
no.
it simplifies it.
Well, it simplifies because you just say subtyping is this function. And you don't say subtyping is, in some languages, it is this difficult procedure that I'm going to specify. In other languages, it's another difficult procedure that depends on memory layouts of some things, and so on and so on. And in Java, it's like this, but it's unsound. And in Scala, it used to be unsound in Scala 2, now it's sound in Scala 3. And I don't want to talk about that. It's too much irrelevant information for practice, where, you know, my goal is not to explain how to design a new programming language. The goal is to explain how to use a programming language. So very clever people have thought about these questions for a long time, and they come up with certain things. Now I want to try to understand what they have. Okay. So I'm trying to simplify. So I totally agree with you that a lot of details are different in specific cases.
Okay. Maybe it, I'm not totally aware of the problem with Java, the unsoundness. If you get a chance, maybe send me a
Right.
link or
I guess
something.
let me post this in Slack, perhaps.
To put it briefly, arrays should be non-variant in their element type, but they are covariant.
Why do you say they should be non-variant?
You should be non-variant because you can change, both read and write an array element.
Oh, well, yeah, if it's mutable, it has to, yeah.
Yes.
You're right.
So yes, you don't have the problem, for example, with Scala lists.
At least the immutable ones.
Yes, yes, the immutable ones, right. I guess there are mutable ones, aren't there? But I've never used them.
All right.
I keep getting up because my cat's making all sorts of noises, but yeah.
Okay.
The other thing this makes me think of is in object-oriented programming, there's this Liskov substitution principle.
Liskov, yeah.
Yeah, which establishes like when a class is really a subclass of another one. And the answer is like when you can safely substitute, when you can use one instead of the other, which is kind of the earlier definition that Sergey mentioned.
But what does it mean you substitute? Which one do you substitute?
Yeah.
I mean, it's really
idea
not
is if,
explaining anything.
yeah, I mean, if you have a function that takes an A and you have a subclass of A, then you can just pass one of those objects to the A and it will work.
Right.
So it will work in a given programming language and in a given context. Then you can say it's a legit subclass.
That's right.
Then right.
Because in some languages you can subclass, but then like remove methods or
that's right.
Things like that.
Okay.
I mean, you can certainly break this. And so that's why they talk so much about this Liskov principle. Don't write code that breaks this. And in one of my later chapters, I have a footnote explaining that if you have immutable data, then Liskov substitution principle is always true. So
if you have immutable,
if all you have is functions on values that return values, then there's nothing to discuss here. Nothing to discuss. The Liskov substitution principle, it's always true. There's nothing to check. It's just automatic. It's not automatic if you have classes that mutate things. Then you have a subclass that mutates it differently. And then
right.
Anyway,
I don't know that breaks, that makes it unsound though. It just means it doesn't work. the way you expect it to.
I'm putting into Slack the links to the paper about
Okay.
sound type systems.
Are you putting it in your science of functional
Yeah.
programming or? Okay.
Yeah.
Oh, there it is. Okay, I think.
Okay. So, okay, I need to drop off now. I will be back.
Okay. All right. Thanks for the discussion.
Feel better.
Yeah. Hello, everybody else.
Yes. So how far did we get and where did we want to pick up?
I
Has it
didn't
been
get very far.
sorry, a question? Has it been posted on Slack? The link to the paper,
Yeah, he
uh,
just did.
or in which channel?
Science of
Functional programming.
Right, that category 3. I don't
Not
see that.
category theory, not dependent formalities, not general, not random.
Okay.
You have the science of functional programming channel?
No,
No.
no. There is another channel about functional programming. Oh,
Yeah.
okay. Okay. Do you know how could I find that?
It might be in general or something.
Let me.
Now I can hear. No. I can see the channel. It
Okay.
suddenly right.
I added you to the channel, so yeah, you should be able to see.
Oh,
Okay.
is that it?
Okay. Thank you, Wayne.
Yeah, no problem.
So you have some hide stuff, right? Okay.
I'm sorry.
So I mean that this group has some hide stuff. So
Channels?
right, the hide the lost treasure, right? So I will. Okay, I will dive in if I. So there are more channels being hide from general view.
Yes. What other treasure is there that we don't know about?
No, this just cat theory, dependent formalities, hot. Well, there is hot,
Right,
random, science of functional programming.
right, and that's all.
That's it.
Okay.
There's a hot channel too. I don't seem to have that one. Now, how do you get into a channel? This is something I don't know.
Me neither.
I think you should be able to search for a channel if you know the name.
Browse channels. Oh, I see. There's a browse channels option and you can join. Huh. All right. Well,
Okay.
most of these messages are from 2017 and I have missed them all.
Yeah.
Okay. All right. I guess I have some catching up to do.
Yeah. Mainly, I think it was Tom, Jack, and myself on it. But
Right. So the plus sign next to the channels control on the left side of the slide page has a browse channels option. And that is where you find all the channels that you don't know about.
Okay. Great.
I see. Yeah. Right.
So I never knew that. Somehow all of the channels that I'm in just magically appeared and I yes, don't know where they came from.
The magic the magic is over. So it already had an explanation of Tammy. Okay.
Okay.
Sorry,
So
can someone remind me how we invite people to Slack? Who does that?
I've been doing it, but I think how do you do it?
Any of us can do it. Maybe I can do it. Who knows?
Yeah, I think so.
We just need like an email address or something, right?
There's like you go to participants at the bottom and then copy invite link. And then you send it, I think. You see what I'm saying?
I don't see participants.
You might have to make your screen wider or
I see
something.
there's an invite people under add teammates. Do you see an add teammates thing in the controls on the left side towards the bottom?
Oh, yes.
There's an add teammates, and then you get an invite people option if you click on that.
Cool. I will try that. Thank you. Leo's interested. All right. Sorry, Adrian, as you were.
Yes. So where were we in the book? Where did we want to pick up? I think we were talking about chapter 6, but I don't remember where we are. I have read as far as about the middle of chapter 8, but I haven't gotten all the way through it. I'm just before the EEC type class.
I've started chapter 8.
I haven't read chapter 8, I'll admit.
I have one random question about chapter 6.
Yes.
Let's see. Let me find the notes. 642. Yeah. So in section 642, there is a type constructor called sum, which is sum A is just 0 plus A.
What page?
This would be physical page 213. Oh, but at the top, it becomes page 227. 213 is the page number at the bottom of the page. The Adobe page number is 227.
Yeah, I agree. Okay. So where is...
I can also share if that will help.
Oh, okay.
But yeah, I wanted to do that since no one else is doing it at the moment. I'm trying to do this. Can you see the preview here?
Right. So
yeah.
This thing. I'm just, I mean, I understand that what 0 plus A means, but I don't understand why you would do it and how you would use this sum, because it appears to be obviously isomorphic to or equivalent to the original type A. Am I wrong?
yes, it is.
Yeah.
Sum is a constructor of option. So the way Scala does data constructors is to create a new class in which the constructor lives, and that is a subclass of the class whose constructor it is. So sum is its own type of thing, but it's also one of the ways to build an option.
Okay. So this is in Haskell, it's called just, the same thing as just, I think.
Yes, yes.
Okay. Cool. So why, I guess I'm wondering in this case, okay. So sum is actually a subclass of option.
Yes.
Right.
Sense. So I guess it kind of makes sense that for parallelism, you would want to use that. All right. Okay.
For parallelism.
Sorry, between 0 plus A and 1 plus A, or alternatively between sum A and option A. It just looks a little, yeah. Because otherwise, right, you wouldn't need that. You could just say A. Right? A is a type of option A. Is that reasonable?
Yeah, I don't know why it is 0 plus A if he's trying to explain how sum A is a subtype of option A. It should just be A is a subtype of 1 plus A.
Seems a little
Right.
simple.
But 0 plus A is always isomorphic to A. And
right.
So Sergey often uses 0 plus A where you would use just A.
Yeah.
I guess that's related to the matrix notation also
Yes.
likes to do it there.
Okay.
Sorry, you're saying?
But in my mind, sum corresponds to A, not 0 plus A. But I guess. we
Okay,
could
well,
look at
that's
it.
the whole point, but thank you, that helps.
But it's the injection though into the right summand. So sum A and A are not the same, right? One is an injection into a sum type, whereas A by itself is not. So yeah, I mean, I have some questions about the notation
Okay. No.
using
Right.
plus to both represent the sum type and the element of a sum type. But anyways, that's for another time.
Right.
Right. So
Yeah.
that
The
notation.
plus really should be union.
Yes, but right, the notation is unambiguous because Scala is a language where you cannot confuse terms and types. They live in different spaces.
Right. Although the same name can be in each of them.
Yes.
Okay.
Well, I really, this is not a question, but I really like that, I think it's somewhere in chapter 6 or 7, we finally prove that the types, which I think are called, polynomial exponential types, the ones that use 0, 1, plus, times, and function. It's their fundamental operation, and you build up anything from that. Those are all functors, right? We want them to be functors, but
Yes.
we prove that they're all functors, and we prove things about the variance of the sub terms within those functors. And, and I guess always this is not a surprise once we've gotten here, because I certainly expected that to be true, but it is nice to see that laid out as a proof, which I think is done somewhere in here.
Right. It is, I think tables, it's in chapter 6. He has the table 6.2, which is constructions that define a functor, and 6.4, which constructions that define a contrafunctor.
What page is 6.2?
Let's see, that is.
Oh, I guess I must have gone beyond it.
It is on page 200.
Wait, but okay. Section the first. Okay.
So is this PDF 600 or page number 600?
It's the printed page number, not,
Page number, thank you.
Yeah, not what Adobe thinks is the page number. Adobe
Oh wait,
is
you're saying 600?
200.
200.
Yeah,
Yes, table 6.2 on 200.
this thing here. Actually, if you search for table 6.2, it'll probably get you there.
I see.
So
Okay,
right,
I think I'm there.
Yeah, that's sort of the summary of most of this chapter. And yes, that is a cool table to see.
Oh, okay. And then there's recursive types, which are a bit harder, but I guess they still.
Well, the recursive types are pretty important types because they are things like lists and trees, and we use recursive types all the time.
Does he go into the positivity stuff?
Yeah, well, yes.
I guess it doesn't matter.
Right. These are functors, and so they are covariant in their argument. if that's what you're referring to.
Hmm.
Um,
I guess so, yeah.
Yeah, it's table 6.4 that lists the ways to build a contrafunctor, which of course is contravariant in its argument.
Table 6.3, recursive disjunctive types.
Right, table 6.3 is just basically a list of examples, but
Okay.
yeah, examples of
There
how
it
to
is.
use recursive constructions to do common things.
Do we know exactly what recursive constructions work, or do they all work?
Right, I'm pretty sure they don't all work in the sense of all being inhabited.
Yeah. Usually there's a, a constraint on how the constructors for recursive type work, like the recursive thing has to appear only in positive positions.
Oh, okay, so that's this part here. But let's see, this must be, I can't select it. It's the last entry in table 6.2. Wiggling on right now. So we can do this if we have a So this now has to be a functor of 2, or this is a bifunctor. Right, this thing S.
Yeah, I guess so.
So that means that in order to use this along with the other rules, we need also a way to construct bifunctors. So I wonder if there should be some discussion of that, and maybe like, well, okay.
That was part of, like, table 6.3 had, where'd it go? Oh, shoot, I lost it. But it had a column that was like about bifunctors, I think.
Right, there's section 6.2.2, which is all about bifunctors.
Yeah.
So I wonder if there are any complications with constructing the bifunctors. I mean, so this is a kind of recipe for constructing all of the functors that we might want. But since we also are relying on, yeah, I wonder if there should be entries to describe the bifunctors as well. And probably the ones that show up in practice are easy and it's not a big deal.
Yeah, the table 6.3, yeah, has that column bifunctor. And it sort of shows what the bifunctors are for list, non-empty list, and so forth.
I guess one thing I'm noting is that there's no function type introduced here, right? So it's only plus and times, no arrow.
They're
Oh,
polynomials.
Not exponentials.
You're talking about 6.2?
No, let's see. Can you see it? What I'm looking at here? This I'm looking. I think we're looking at table 6.3. Specific
Yeah,
bifunctors
6.3.
that are used for practical purposes. And we're noting that.
Can you make it a little bigger?
Yes.
Yeah, thanks.
Good. Yeah.
Yeah.
Yeah. So someone was observing we have no function types in here.
Yes, I wonder if there are any practical.
Well, this is recursive disjunctive type, so I guess he's focusing on the ones that have plus. But you know, you can have a you know, like a tree kind of thing where, you know, one of your nodes is like, you know, something arrow A, where A is what you're trying to define recursively, right? So you could have sort of a, you know, maybe bool arrow something, and you know, so that way you have two trees at each point. Does that make sense? So you can have, I'm just saying, you can have arrows in your functors.
Yeah, I mean, in tables, I just noticed in table 6.4, which is 2 pages later, we do have the arrow, the function type, in defining a contra functor, C super A. So it does come in, but there are variants now that matter. So L is a functor and H is a contra functor.
And so you have a similar construction for a functor.
Yeah, it must be.
Yep, but it's the other way around.
Yes.
Right.
But yeah, I'm wondering what happens if you try like really funky recursive functors. Sorry, really funky recursive types. What happens there?
I think it's okay. I think you get a functor if you do the recursion with a what's the word? The non-recursive functor in the position of the result type of the function. I think that gives you a functor like as it would in any other position.
Say that again.
I think you can recurse in the result of a function part if you're looking for a functor. Because that should give you a functor.
If we took for S of A, C of A, it looks like we could just take function for that, right? What if we define this S to be A arrow CA? Or rather, yeah. Does that make sense? Because it seems to have the right variance, right? We need to have a contra, it needs to be contra in the first variable and co in the second.
Yes.
Which sounds like HOM, right? HOM is the classic thing that does that. So
yeah,
maybe that would work. Oh, but then we have a problem. Okay, then we get an infinite regress. That says that a C is an arrow from an A to a C, and you can never get to the bottom. Maybe that's why the disjunctive part is important, right? Because you need a case to a case to start with.
Stop. Yeah.
Yeah.
So maybe it's a functor, but not a useful functor for programming, something like that.
You would want to combine it with like the disjunctive case, and then it might be, then it would be useful.
Oh, okay. How about 1 plus A to the CA? Sorry, 1 plus A arrow CA. Should I like write this down? Anyway,
Yeah, maybe.
I think so.
Okay.
That should work. Let's see. Let me try that. Annotate. Annotate with drawing.
Yeah, I mean, I have trouble trying to, think through using his syntax, his notation, because I'm not used to it. So I'm not exactly sure how S is working here.
Hello, I'm back for now. So every superscript, you just put the Scala square brackets around that.
Mm.
So S square brackets A, comma, C square brackets A.
Ah.
So each superscript opens a new scope of type application.
Yeah.
So it's comma, I use comma specifically, so it's not often needed. But, I don't want to use space.
So, right. I think what Hugh's asking about is, could S be a function, the function functor kind of thing?
S. Yeah.
Sorry, when we construct a recursive type, I'm wondering if we can construct weird recursive types, or like how weird they are allowed to be.
No, so this is not, so see, I need the recursion with respect to a specific type parameter. And with respect to that type parameter, it should be positive. Now, can it be a function type and still positive? Yes.
Right.
So some situations restrict type recursion to only polynomial type recursion. You're not allowed to use functions, but I don't restrict that. And in fact, there are use cases for this kind of recursion. It's very important that it's positive, so it's covariant with respect to second parameter. But for example, consider a lazy stream where the next elements are evaluated after the previous ones are needed. So then that can be implemented as a recursive type where there's a function before the recursive type parameter. So then you have to call that function in order to get the next nested recursive type now. Then you again have to call that function to get the next one. So this is used in code in libraries to implement lazy streams. So I don't see why we need to restrict it. There are certainly situations where you have to be restricted to polynomial recursion. This is too early for those situations. You don't have to be restricted. Yes, you can get quite a weird recursive types doing that, but they will be lawful functors or contrafunctors. So from that point of view, you're fine.
So probably this one is an okay contrafunctor.
Yeah,
makes sense. I think so. You can either have the unit, or you can have a function to unit, which actually is not that interesting.
Well, you can, instead of unit, you can just say
something more interesting.
P,
yes.
say P.
Yeah. Okay.
And then you have an interesting value where you have P plus A to C.
So we're doing contrafunctors here. Okay.
Yeah, we're in the contrafunctor section, which maybe we shouldn't start there. Maybe not the best thing.
No, it's kind of a mirror image of covariant. There are fewer contrafunctors in some sense.
So you pick some type P, and then you say, okay, this type will be maybe any 0 or more functions from an A, all leading up to a P. Anyway, apparently that's an okay. This disjunction of all of those things is an okay contrafunctor. Type constructor, which is a contrafunctor.
It will be contravariant in A.
Yeah.
So you will be able to define a contranet with respect to A and satisfy those.
Cool. All right. Well, that was an idle question, but that does help.
Right. This is a type that consumes an unknown number of A's in order to give you a P.
Yeah. I guess you could also write that as
once you start
A to the something.
Eventually you will get a P.
Right. Yes. Eventually you should get a P, but you don't know how many P's it's going to eat before it, or how many A's. Before it
Well, it's like a stream. It's a stream. So you consume an unknown number of elements.
Right. It's an anti-stream. A stream produces an unknown number of elements.
It's a consumer, maybe a sink.
A sink, yes.
Yeah,
But it gives you something back at the end.
Eventually the sink is full and finished.
Yes.
So consumed enough.
Then it returns a status.
Needs to be cleaned up. No, it's for me actually this approach where you just write some weird examples, but all these examples follow scheme. So you have products, co-products, exponentials. You have substituting type parameters, and you have recursive type. So in every case, I tried to find out if there is a construction that gives me a lawful type class, for example. The same, we would do the same for filterable functors, applicative functors, monads, or something like that. So you just try to see, can I construct new ones out of old ones, and if yes, how? Every time you satisfy the laws, then you have a kind of intuition. So, oh, there is just a whole load of functors here. When somebody gives me a functor, it could be any one of those. For example, it turns out that every contravariant functor is applicative. Anyway.
Are there any other questions showing up from the reading that I could scroll to?
Right. So are we done with chapter 6 then, I guess? That's a big question.
I have no more questions about it.
Then did we want to look at chapter 7, which is, I guess much of it is a recap of the notation that we have seen.
I think one comment I had much earlier was that the superscript where you have the colon, sometimes I don't see the colon. You know, it's like if the font's like smaller, like on my iPad or something like that, I have to like zoom in a little bit to see it. But I guess once I knew it was there, I knew to look for it. But at first I didn't. So,
and it does change the print quite a lot, right? You don't want to if you miss the colon, then it becomes a completely different type of thing.
Yes.
Better they use double colon, like Haskell.
Ah.
So it's kind of in your face.
Or bolded or something. But no, it's
Ooh.
too much work. I mean, it's
Ooh,
okay.
No, it's not too much
just
work. It's a script that I will run on it to bold it. But yeah, I don't know. Yeah, it's a question. I mean, this
so
is
just a very side question. You use how do you pronounce it? Links? Is that right, sir?
Licks.
Licks.
Mm-hmm.
Can you just, is licks good enough that if you like edit the code that it, the tech that the LaTeX that it produces, it can like read it back and deal with it?
It can, unless you are doing something weird with macros and so on. It should be able to do that. There might, of course, there's no guarantee. LaTeX is a Turing-complete language, so but hopefully, if it's taking its own.
But like if you fix a typo, just using
for me, it's easier
LaTeX tools, then it would just read it back in, and everything's fine.
Okay, yeah, it's true. It's just that it's not easy to merge different changes from different people in this way. So I'd rather do it manually. You can do you can do a PR, changing some LaTeX, and then I can go over it and put the changes manually in. It's just that, you could presumably do a PR on Lix itself, and then the problem is to resolve conflicts.
So I haven't used it much. Like for table 7.1, does it actually show it to you like the way we're seeing, roughly the way we're seeing it here, or table 6.4?
You see tables mostly as you see them here. I'm not sure I can try to share the screen.
Okay.
I'm not sure what's up with.
Hugh, maybe you need to release.
Oh, yeah. Like that.
Yeah.
Okay. Yeah.
Okay.
So where were we?
Like 7.1 or something.
7.1. 7.1. Right. So that's what I see.
Right. I see. Okay.
There are some stuff here. There is some stuff here that is kind of LaTeX replacement like this. So on. But
it's inserting that for you.
Yeah. Yeah, that's what so I could do a lot of stuff on this. I could get, for example, so here's an equation, this matrix. This is the code, which is not syntax highlighted until the end. So here I don't see the syntax highlighted. But it is syntax highlighted at the end.
Is it
Um,
under the covers? Is it using something like, what
no,
is it,
it's a LaTeX
listings?
package. It's listings, yeah.
Yeah.
It's a LaTeX package, but it does not get processed until the end.
Mhm.
Then let's see. See if I have any kind of diagrams I can show. Sure. So here's a table, for example. So code
Mm.
blocks and math. Let's see if I have a diagram. Let's see if I can diagram somewhere.
Maybe going back to 6.2 bifunctors, you had some diagrams there.
That's right. Okay, so diagrams using a diagram package look like this. But what I could do is I could
So is
wrap
it using whatever it was, the
Mhm.
component, I don't know what it's called.
And there's a way of doing this differently. Preview, I think. Let me see if this works. Mm-hmm. Let me see. Okay. Show you this. So in any case, this is LaTeX for the diagram, but there is a way of let's see, there's a way of inserting kind of a preview of it. Trying to, okay, never mind. It's just taking too much time. Oh yeah, I know.
Right click.
I know what's going on. It was telling me to reload from the file, and then I can do this.
Yeah.
So if I want, I can make it preview just this diagram, and I can look at it. But if I want to edit, then I'm back to this. This is essentially LaTeX.
So is it basically then calling LaTeX to generate that diagram?
Yeah.
Okay.
So if I want always to see that, I can do that. But editing is possible only using the LaTeX code. And so that's for diagrams. Similarly, for any kind of very special structures, but most common structures are displayed. Trees, for example, I think I have
like that
trees.
table you could edit directly. Is that right? You don't have to.
Yeah, that's right.
Yeah. Okay.
I can edit that table directly. So it is not a preview of a table. So I could make it a preview of a table to look a little different. And so that's the thing. Here, for example, this is a tree. But actually it is a LaTeX code, which I have to edit.
Does this also generate HTML, or is it just purely?
No, it's supposed to, but it never works.
Okay.
This kind of complexity just breaks. I was trying to do this and I gave up. Simpler things, it works.
Yeah. I was trying to do it too in a different way, and it just keeps getting awkward as soon as I start doing more stuff.
It's just very hard. It's just very, very hard. It's better to produce right away some kind of markdown and not even use tech.
Right, but then it gets hard to do.
Oh, you can do markdown math nowadays.
Yeah, okay.
But of course, it's very limited. So here, for example, I have references to equations. Like I have references to figures. I have, for example, here, there's an equation with a number, but actually it's a symbolic label. So this equation can be referred to by the symbolic label, and then the number is automatic.
It's filling in the number just to tell you what it is.
Yes. Yeah. But I
That's
can
cool.
edit this and I get the symbolic label. So anyway, that's the answer to your question. Let me check on my daughter. Actually, I'll be back.
Okay.
Let's see, do we have anything else to say about chapter 7? I confess I still find the matrix notion less intuitive than just writing out the equivalent thing in program notation or Sergey's more concise notation, and just looking at it linearly rather than as a table. But that is something I guess I need to get used to.
Okay, so like that, use a disjunctive value entry in 7.1. This one here.
Right.
Yeah. So I guess this is also the pipe. So you're sort of saying take a P that's a sum, an either, and pipe it into this matrix.
Right. P match, blah, blah, blah.
Okay. Yeah.
P match, case A, blah, 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 case B, blah, 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 returns a C.
Right. So I guess if you had a P, an actual P, then it would be a 2-column matrix. And then when you multiply them, you sort of get the right thing.
Right.
Okay. Pipe notation. Okay.
Pipe notation is certainly convenient, but it's the same sort of thing that we can find in Haskell.
Right. What do they use there? Like, is that dollar? No.
Dollar is the other way around. But is it vertical bar greater than, or am I thinking of another language? Anyway.
That might be another one.
I'm not fluent in that.
It's like swap apply. It's like swap and function application, right? Function application, but the other way.
Right.
I don't remember the symbol. I'm sure there is one.
Yeah, I'd have to. Okay. I was, Okay. So what is this?
One
Go ahead.
one use of notation that I find might be difficult for beginners is the use of the symbol 0 to mean both the constant and the constant function. So like in this, at the top of your display, compute composed with get, you have this, if it's into the injection of the 1 and the result is 0 for that part of it, which means it doesn't exist. but that actually should be a function that returns 0, right? Because the one on the right is, if you give it 1, then I return 100. So this kind of abuse of a symbol for both the constant and the constant function, I find needlessly confusing here. Maybe a simple symbol like a hat to refer to the constant function might have made things a little easier.
Are you talking about this and this, like, because they're different symbols?
Yeah, I'm talking about on the left side.
Oh, okay.
0, the occurrence of 0.
Oh,
what
the
is
0.
the meaning of 0?
Hmm.
Right? 0 is the constant in the type null, right? I mean, empty type.
No.
So when you see a 0 there, it means there is nothing on that side, right? There's no injection onto 1, is missing. But it doesn't really mean 0. It means the function that returns 0, I think.
No, that is not what it means. It does not.
No?
You cannot return or this particular function for the for neither case does it return for neither case does it return a none. So that's really, there's nothing there. There's not even a function there.
It's true.
Then
As long
why
as it's an
then
empty
why
type.
put the 0? Then why put 0 there?
Because that's how Sergey does it. These matrices
right?
are sparse in the sense that there will be only one thing per row.
Yes, that's what 0 means. 0 means that there's nothing here, right?
Right. There's
but
no
then his notation, he uses the plus constructor to mean 0 plus x means there is no 0, it's just an x, right?
Yes.
So in order to make that notation consistent, you have to put something there. The question is, what is the meaning of that 0? And to me, it has to have the same type as the one on the right. 1 arrow 100 means it's a type, a function, right? So,
but when you say 0x, it doesn't have the same type as x, because x is in an inhabited type. It's a value from an inhabited type, whereas 0 indicates an empty type. So they don't have the same type in that case.
Right. This is the output here is a disjunction. So the two possible return values should be of different types. So the first possibility is unit, which never actually gets returned, and the other possibility is int.
Okay, hold on. If unit, doesn't unit contain a single object? And are we not representing that object with this script 0?
No, unit is 1, right?
The unit is.
Okay, what inhabits the unit? What do we call that singleton that's inside unit?
I don't know what he calls it. It's probably 1.
Okay, I thought that's what he's using 0 for here, which is a little bit of an overloading, right? Because 0 means both the empty type, the none type, but it's also the unique element of the 1 type. No.
Sorry, I'm back to no.
Okay.
So the number 1 is the single element of the unit type. So
I see.
If you find a notation that is,
in that case, I don't understand why you put the 0 there in that first top left position. That
You
there's
wanna share?
nothing.
that nothing is being returned. I don't want empty
Okay.
places in the matrix. I don't want to. I could leave them empty, I suppose. But
That
then
would be
it's,
even more confusing, but
yeah, exactly.
yeah.
So I cannot put anything there. So the 0 means this absence of value.
Exactly. But that's the problem, right? We have a,
Oh, I
in
don't
this
know why is that a
notation,
problem. So let's see.
You want to share?
Let's see. I'm trying to do that.
I mean, I realize that this is not the main point of your chapter here. It's just, as a beginner, unfamiliar with your notation, to me, that would be a sticking point, is what does this mean, right? And you're hand waving a little bit here in order to get going. But to me, just the first step is a little bit of a problem. Right, this is the type, but what about a value where you use the plus to mean disjunction value? Like 0 of type string plus 0 of type int, for example.
He's just right.
So-
Right. So this is the notation I'm using. Let's add a string here.
To use plus both for the type and the value. Okay.
Yeah, which again, I find it a little bit confusing, but nevertheless, okay, let's assume that we can disambiguate easily.
Wait. So actually, shouldn't X1 be one of those things? It can't be. I don't know what that means anymore.
Right, only
Right,
one
shouldn't-
can be non-zero.
It is one of those things. It's just that
Oh, but the other ones are 0.
possibilities, yeah, the possibilities are being
Okay.
enumerated using the plus. You know, it could be 0 of type 1 or 1, 2, 3, or another 0 of type
I
string.
see.
And my question is, what does 0 of type 1 mean? Right? It
I think
means basically you can't have anything, right? It means you cannot
Right.
have that one. You can only have the middle one.
Right, you don't
Right.
have it.
it's a placeholder indicating an absent value.
Yes, okay.
You're actually right that this notation does suggest that the bold 0 is a value of type bold 1 or of type string or whatever like that, but it isn't really. It's just it's a gap where you might have such a value.
Yeah, but you know that nothing is a subtype of anything. So
Yes.
you are allowed to do that kind of thing. So I am overloading. So here's on the right, I have written the Haskell-like notation,
Mm-hmm.
right?
Exactly.
Which has
Right. X.
the same value, right? So why do I use this notation? Why do I use
Because
Then you could
you
do the
also use-
multiplication.
Because you also use 0 bar as the null type, right? In the type hierarchy. It does represent the type that has no elements.
Empty type.
So
Yeah.
I don't have a symbol for elements of that type because there aren't any.
See,
So
I wonder
decided-
if you should use another notation for the
Which one?
emptiness.
Maybe
Like maybe
epsilon,
the empty set, maybe,
empty set.
or
Yeah.
even a bar under, just a regular dash. But anyways, yeah, I don't know. Overloading the
Yes.
0 to me seems kind of confusing.
To me, it's just, yeah, well, it's overloading, but 0 is a very special thing. So
Right, it is an unambiguous notation because 0 as a type will never appear in the same context as 0 as the absence of a value.
I guess it's implicit in this notation that the values in the plus expression follow the same order as the types in the plus expression, right?
Yeah, that's important.
Right.
And similarly, the vector components must be in this order for the matrix notation to work. So if I have a function from this type, x, I have some type y. So int plus int, right? I have a function x to y. I have to apply f of x1. Right? So how do I write that? So I write the function f as a matrix. Unfortunately, in this whiteboard, I need to get smooth things. Okay, I need to go. Sorry.
What just happened?
Yeah.
Okay. They're all figures that you can move, I guess.
I'm sorry. This doesn't work. I will open back later. Stop this.
So you would represent your function f as a matrix.
Yeah,
with
I'll have to
one int and string going down and int and int at the top. Is that right? Something like that.
Right, that's right. I'll be back.
Okay. So for something like this, what's really happening is that you're sort of multiplying 0 by 0 or something, and so there's really like a 0 plus in here, right? But the 0 plus goes away. Oh, is Sergey gone? So, I mean, if you do matrix multiplication, you'd multiply this row by this column, so you'd get 0, and then you'd get, I guess, plus ID of after this. But the 0 he doesn't represent, it just goes away.
Right.
Or you just don't include it, I guess, whatever, you know. Okay. Anyway. So, for next time, should we restart with type classes, chapter 8?
I think so, since we haven't actually discussed it. Type classes are a pretty interesting way of, in the abstract, saying that a particular type has some properties, which is to say some facilities that you can actually use with that type. So yeah, there's a lot to be said about type classes. So Yeah, does that sound good?
Some-
Chapter 8 for next time?
Yeah.
Sure, we could start it now, even if we're really done with chapter 7.
Do you
Uh,
have things, because you did read some of it, right, Hugh? So do you have
I did.
questions? Or?
Yeah. Oh, that's right. Yeah. Sorry, I don't want to jump ahead. Don't want any spoilers.
Oh, okay.
But there aren't really spoilers. Actually, the last 2 exercises in chapter 7, I found interesting. I thought I understood them when I looked at them, but now I'm not sure. But I can do
725.
yes.
So what are you talking about?
The very last 2 exercises in that section.
I mean 7.2.5.8.
Yes.
Yes.
9. There's a flatten, which I guess is hinting at a monadic.
Yes, it is. Right. So you have this.
I share it. I'll share it. Is that okay? I don't want to be
Yeah.
jumping ahead to chapter 7 and like stressing people out who haven't read it, but it's I think it's fairly harmless. Let's see. There. Yeah, so it's these last 2 here.
Right. So you have
Yeah.
this is roughly the same structure as option, except that instead of the none case, you have a pair of ints.
Yes.
So you flatten it the same way that you would flatten an option. That is, if you have an option of A, you can convert it into an option of A.
All right. I don't think I want to write that as a matrix, but just intuitively, if you have something which is either a pair of ints or a pair of ints or a value of A, then if it's one of the first 2, you have a pair of ints, and if it's the last one, you have an A, so that means you get either this or this, and you have one of these. Boom.
Yes.
Cool.
Yeah.
Flatten.
Okay.
And then flatten is a. Have we talked a lot about flatten as a concept? I mean, I guess it was back there when we were doing like reduces on sequences and stuff early on in the book.
It's kind of what we were just talking about. It's like if you have an f of A, how do you turn it into an f of A?
Okay. So it is a function. Okay, so it is a function of this type. So it's an L to the, here, I'll write it. Annotate. So this is also L, I believe. L.
Can you just share just the preview instead of your whole screen? It might make it bigger.
Oh, I can try. Let's see. Okay. Just that window. How's that? I can also blow up the type size if that'll help.
Maybe you have to click on it or something, because we're still seeing dark.
Oh, but why? Why? I'll try again. Share screen, preview, share. Your screen sharing is paused. Oh, resume.
Oh, unpause it.
Well, screen share.
Where it says pause, there's probably a button that says unpause.
There is a button that says resume. I'm clicking it.
Oh, okay.
You are using,
There's a message saying you have started screen sharing, but apparently it is the null screen sharing.
yeah, I'm sorry, that does not appear to work.
Okay, sorry.
I want to go back to the whole monitor and try, oh, I lost my typing, my drawing rather.
Oh, sorry.
Okay, I'm gonna get the, that
Okay,
better?
thanks. Yeah,
Even, whoa, what happened?
side by side mode. Go back to view. Yeah,
Okay, but now I'm, sorry.
just go down a little bit. There,
Yes. That work?
that's good.
I know I seem to have the worst eyes of people at work, because whenever anyone does a presentation, it's always me raising my hand and saying, could you blow up that? Anyway, this thing, I believe, is also a function from in this notation. It's like this.
Right.
Right.
Okay.
So if you were to parenthesize that, right, it's really like in cross in plus parenthesis, in cross in plus a.
Yes,
But yeah.
cool. And then
Okay.
flatten is not only a function, but also, I'm guessing, a natural transformation
Yes.
between the functors L of blah and L of blah, or L squared and L.
Right. And the proof ought to follow the same shape as the proof for option.
Cool, which I have not done, but it doesn't look hard. Or maybe it
So
was
what's
done.
that? What's the notation F of up arrow L, up arrow L?
Yes, I thought that was a mistake the first time I saw it.
That means
Lift.
right.
I think it might be something like
The upper L is using L's F map
On F.
on F. Yes.
And then
So
you're doing it again.
If we write it in a mathematical notation, it just means L applied to L applied to F, right?
Well, not
L
L,
of F.
not L the type constructor, but L
No?
the mapping operation.
Well, yeah. In category theory,
Right.
often the L can be used both as
Yes.
the functor and the F map. So I think
Yes.
if in that sense, it's the L applied, but yes, but it's really F map.
So the part in parens is LA to LB. Anyway, yes, I agree. So this whole I'm going to erase that. I think that's confusing. Yeah, so
But that I didn't really know, this naturality law. I'll have to think about that.
yeah, I don't think I did either. So yeah, L of F is another way of looking at it. And okay, L of F. So what is its type? I'm a little lost. The thing in here, this is now a function from L of A to L of B. This thing in the green parens.
It's a function from int cross
right.
int plus A to int cross int plus B, right?
Yes. Sorry. Try this again.
Well, actually, it's 2 lines above. Right, that F, it's
F is
that line, that's sort of saying that what that lifted it, the type is.
But this whole thing, type of this,
Right. It's from L of L of A to L of L of B.
right? So then you should be able to do the second step here, which takes you, collapses the L, takes you back to L. Right. Okay. So over here you have L, L, A, 2, L, L, B.
But when you flatten it as the first step, it's just an L of
Or,
B.
right. Thank you. Just to L, A.
Sorry, L of A, rather, not.
Now you can do it to L of B because that's what the lifted F does. Okay, so these things do in fact have the same type. Cool. All right, I imagine the proof is trivial and we could do it in our heads if we're really, really on the ball.
I'm still confused about that F up arrow L up arrow L.
Right, the parentheses are, yeah, where Hugh drew them.
Are the parentheses correct? So F up arrow L.
Right.
Now I'm confused.
And shouldn't that end up being a in cross in plus B, and then you're trying to flat map that with F? That doesn't work. I mean,
Well, no, you have to apply the other up arrow L first. So F is an A to B. F up arrow L is an L of A to L of B. F up arrow L is an L of A to L of B.
Ah, that's nice. Yeah.
oh, okay.
Up arrow L it again. It does the same thing. It
Yes.
it puts an L
Applies an L to each
underneath
of
it.
the two
Yeah.
types.
Okay, I see.
But yes, it is a little startling when you first see it, I think.
Okay, and then the flat just takes it back to L and B, right? The
Yes.
flatten. Okay.
Cool. All right, well, I should probably work through that in my mind just to convince myself. Does anyone know what the star means? Out of curiosity, maybe it's mentioned in the beginning of the book or something.
Where's the star appearing?
Sorry, on the
Yes.
Oh,
that's number there.
I don't know. Difficult.
Too difficult, too easy, fundamentally important. No.
Copyright? Who knows? Anyway, I'd like this exercise sort of jumped out at me, or this pair of exercises as a bit more interesting, perhaps a bit more interesting in a categorical or mathematical way than most of them.
Yeah, because this is introducing the monad nature of L, right?
Yeah. Which I
And
guess.
and flatten is one of the two operations of a monad.
Yeah, depending on how you want to set up.
Yeah. And that last exercise is basically showing that you can, that the flattening can happen, the outside in or inside out, depending on where you are. So
Yes.
Yeah.
So do we want to take a quick look at the start of chapter 8? The first beginning of chapter 8 is basically talking about how to build type classes in Scala.
Yes, it's very Scala heavy.
It is
I don't
very
know.
Scala heavy.
I,
Yeah.
I don't know you guys' opinion about this part, but I always find that part is mostly about Scala is a bit distracting. It's actually the later part that when you start talk about like extractor and how do you do the construction of extractors, that seems to fit in more of the theme of the book, which is talking about functional programming. But I find that when I talk about the implicit syntax in Scala, I feel it's just a limitation of the language. Maybe it's just my personal opinion.
Yes, I mean, Scala, the way Scala does this does seem a little messy,
Yeah.
but you know,
But it is messy. But
well, I mean, I guess some of the whole idea of implicits is messy in the sense that it's adding something to the type checking that is not there in conventional languages. I mean, what you're doing is you have a regular type checking context, which tells you about the things that you have declared in the current scope. But in Scala, you also have this sort of database on the side of things, of values that you have declared implicit and that you can use to automatically fill in any implicit parameters. And so it's not a
and it's searching by type.
Yes, and it is not a concept you find in simpler languages, although it is very similar to the way Haskell does type classes.
Yeah, these implicitly things are like I think they're called polymorphic constants in Haskell. So like if you're in the context of a monoid and you want to do the monoid identity unit, right? The neutral element. I forget, it has a name, whatever it is, like identity, let's say. And if you just say that in a context that makes it clear you need a value of type X, then it will look in that type X for a corresponding thing, and it will just drop it in.
Yes, yes. In Haskell type classes, when you use a type class, if you think of a type class as a sort of module, it actually imports all the names from the module, which Scala does not automatically do. So if you look at the uses of type classes, when you have an implicit parameter, you tend to treat it like any parameter. You just say p dot whatever thing you want to get out of your type class. Whereas Scala or Haskell lets you omit that.
Yeah, and unfortunately, Scala 3 has reworked this, implicits with new syntax to make it a little bit simpler. And so this whole section is only for Scala 2. So, I mean, personally, I found this implicits way too complicated because of the very notion that things are happening behind the scenes and you sort of have to keep in mind what's going on, that the automatic type coercion can be invoked by the compiler. If there is an object, a function that takes A to B, and you expect something to be of type B, but you give it type A, then the compiler will says, oh, I'm going to use this function and convert it. It's like, what? I
Yeah.
don't know.
So that's
But
a
it-
field that Sergey hasn't mentioned, at least as far as I've read. But yes, that makes things very exciting.
That's the
Yes.
implicit coercion.
Yes,
Yeah.
You
implicit
have to
coercion.
declare it that way, right? Yeah.
You have to have a function that does the conversion from A to B. It has to
Mhm.
just exist, and there can only be one in that scope, et cetera, et cetera. So I don't know. It's, to me, this whole implicit is solving a complexity that was introduced because you want to, avoid copying parameters explicitly, right? Explicitly passing things through. But it just makes the program, I don't know, unreasonably
Yeah.
more complicated.
I'm curious, is Scala 3 is certainly, we know quite a lot about Scala 3 because he mentions it in the book fairly often. Is it already available? Is it in common use?
It is available. I don't know how common it is because there's so much code that's just Scala 2. And I think there is a conversion way, but I don't think it's backwards compatible. And so, I mean, the syntax has been a new indentation as structure syntax has been adopted for Scala 3. So now Scala 3 looks kind of like Python code most of the time.
Python, yeah.
And
Which is
so
okay
it looks,
with me.
yeah, it looks very different now. And I don't know what the adoption rate is. I haven't done Scala in a couple of years, so.
Cool. Well, it's
But-
obviously very
but-
powerful. It's got like all of the, not only all of the sort of regular procedural stuff that I expect, but also, a lot of the functional stuff that I might want. But so clearly it's versatile in that way.
Yes, definitely versatile.
So I guess in Scala 3, probably you wouldn't have so many curly brackets. You'd use indenting instead.
Correct. And I listened in on the discussion they had back and forth about the indentation syntax and how to make it an ambiguous, et cetera, et cetera. And it was crazy. It's like these bright Scala minds going back and forth about whether to, put a colon at the end to indicate that the following is a block, or whether to use dot dot, because colon is used as a type signifier. And so, but then dot dot may be too small. And so then should we use a keyword like with at the end? It's like, the syntax discussion to try and disambiguate it and to keep it's like, I don't know. Coming from somebody from the closure side where syntax is trivial, everything is an S expression. To me, I found the mental energy required to try and justify one indentation scheme versus another. I just felt like this is just, taking the language in the wrong direction, right? Instead of simplifying, you now have very complicated offside rules, just like Haskell does, right? Haskell also does indentation, but then when do you use the when? Does it apply to what expression does it apply to, etc.? The offside rule.
This is fun, but I want to schedule our next meeting.
Okay. We have 2 minutes left.
We have 1 minute left, according to, yes.
Well, right. I looked at the wrong clock.
So yes, there is lots more to say about type classes, and we should say it next time. So 2 weeks from today is Christmas Eve, and I'm assuming that's not especially convenient for people.
Yeah,
And
that wouldn't work.
New Year's Eve, which again is great. How about the 7th of January?
It might work. I might be on the road.
We can push it off to the 14th if that is close.
Either's fine with me.
All right, let's say the 14th. Give ourselves a nice break in which to learn everything there is to learn about type classes.
January 14th, same time.
Yes.
Okay.
Okay.
Sounds good.
So see you all next year, and I guess we will do chapter 8.
All right.
Okay.
Solstice.
All right.
Happy New Year.
All right. Happy New
Okay.
Year's. Happy solstice.